A brief introduction. I'm Jeff King, the UK Sales Manager for Process and Laboratory Instrumentation for HAC. And today's webinar will be presented by Stuart Ainsworth, who's the UK Application Development Manager for Real-Time Control. Stuart will be supported by Martin Butterfield, who's also an ADM for Real-Time Control. The format of the webinar will follow a 30-minute presentation from Stuart. Today's topic is Advanced Ammonia Removal Control, and Stuart will really be focusing on how you can minimize the risk of ammonia compliance failures via simple upgrades to your wastewater plant. If you've got any questions to ask, then I would please ask you to do that via the Q&A box, which is at the bottom of the screen. And at the end of the presentation, we'll address all of the questions that everybody puts forward. So I would just like to thank you for registering once again, and I will now hand over to Stuart.
Okay, thank you very much for the introduction, Jeff. Good morning and welcome to our webinar on ammonia removal control. The aim of the presentation is to share some of the experience we've gained from working with water companies within the UK and across Europe and the USA. I'm going to touch briefly on how the water industry has arrived at its basic control strategy and how that philosophy has become less applicable to meet more stringent regulatory consent limits. I'll outline two specific scenarios that routinely trip up conventional DO control systems and describe how greater operational control can increase the potential of your existing assets and, most importantly, actually manage compliance risk in a meaningful way. Finally, I'll illustrate how simple it is to convert an existing activated sludge plant to advanced control, or to put it more simple, actual control. So what control system is commonly used now? And why? Put simply, it's the same system that has been used for the past 50 years. That is, to fix the dissolved oxygen within the aeration basin at a constant set point and allow the ammonia leaving the ASP to vary. The oxygen transfer efficiency has been improved through the use of more efficient blowers and diffusers. Dissolved oxygen sensors have become more robust, but the fundamental control has remained the same. During this time, ammonia analyzers and filtration systems have also improved beyond recognition. While these other improvements are welcome, it doesn't alter the fact that for very large parts of the day, far too much oxygen is used with a significant energy cost penalty. When the activated sludge plant actually does need to provide elevated oxygen levels to deliver the correct treatment intensity, the fixed DO set point is set far too low, and ammonia breakthrough is the result. So in practice, the fixed DO set point is the worst of both worlds. It's both energy hungry, and it places a false performance cap on what the activated sludge plant can actually achieve, increasing compliance risk. To be fair, historically, a fixed DO set point worked well when considering a carbonaceous only ASP. Provided there's an excess of oxygen, the rate at which the COD or BOD removal occurs is proportional to the COD or BOD load hitting the plant. So as the BOD load onto the activated sludge plant increases, the treatment rate automatically increases, allowing the full potential of the site to be utilized. Unfortunately, we no longer live in a world where we only have to worry about BOD and solids entering the river. Instead, we have ammonia limits, and over the last decade, we have very low ammonia limits. And that's a problem because ammonia treatment behaves in a fundamentally different way to BOD and COD removal. The treatment rate for ammonia is by and large independent of the activated sludge plant ammonia loading conditions, but instead is directly related to the DO concentration. So if a high ammonia load is presented to the plant with a fixed DO set point, instead of the treatment rate automatically increasing, as is the case with BOD, the removal rate remains static and ammonia breakthrough can easily occur. In practice, the ammonia concentration and retention time within the aeration basin is always changing, so a static ammonia treatment rate or fixed DO set point is far from the ideal. Put simply, using a blind fixed DO set point as a surrogate indicator to treat ammonia is a risky strategy to manage compliance. and for low ammonia consents, I would argue that it's simply not fit for purpose. So what behaviours does the use of conventional DO fixed set points drive? Generally, the operators will see more stick than carrot. That's to say, there are no personal rewards for saving energy, but a clear disincentive to have a failing site. So the operator will want to operate with a high DO set point to be on the safe side, say 1 or 2 milligrams per litre of dissolved oxygen. Often the DO set points are passed on by word of mouth and not actually based on any process information if it's available in the first place. Importantly, there are certain load conditions which may require a much higher DO set point, say 3 to 3.5 milligrams per litre. But the operator has no way of establishing when these levels are required. So these events cause ammonia breakthrough, and instead of the plant automatically providing the correct treatment rate, a long autopsy is carried out to establish what the actual problem was. Furthermore, because the operator has no visibility of the loads hitting the plant, it's not always easy to manage returns or make the correct decision when considering things like tankered imports. This lack of visibility leads to the plant's treatment capacity being much lower than could actually be achieved, because although the common set point of say 1 or 2 milligrams per litre is relatively high for most parts of the day, certain environmental conditions require significantly higher DO set points than the normal, giving you the worst of both worlds, both under and over treatment in a 24-hour period. I'll now outline two specific scenarios which illustrate this problem. The first compliance risk is an event we see time and time again. Storm conditions following an extended dry period. Remember, hackers commissioned hundreds of control systems and has had visibility of enormous, high-quality data sets, a privileged position which really enables us to understand and provide solutions to the water industry. In this scenario, the primary tanks contain sewage with little dilution from sewer ingress or rainfall dilution. So when a storm breaks within the catchment, the flow conditions rise sharply and the relatively high-strength volume within the primary tanks are pushed rapidly onto the biological stage, well before the stormwater has a chance to dilute any of the primary tank effluent. This has the effect of reducing the time available to nitrify and placing a very high treatment rate requirement. In these cases, conventional fixed DO set points of 1 or 2 milligrams per litre will not provide sufficient treatment, and high concentrations of ammonia can break through into the final effluent. Importantly, composite sampling completely obscures the true compliance risk associated with these events. Composite samples always flatten the extremes of concentration within the final effluent, and spot samples are often treated as outliers or sampling error. In other words, ammonia compliance can be at the mercy of the weather conditions and is not effectively managed using a fixed DO approach. These extremes of weather appear to be occurring more frequently too. The second example is again related to the specific ammonia loading rate of the ASP. In this case, it's related to high-strength liquor returns rather than high flow rate. Commonly, it can be centrate from sludge dewatering, but trade effluent and tankered imports can also cause a similar issue. As fixed DO set points don't take into account the treatment rate that's required, these returns can often overwhelm a plant that is not optimized to deliver the full treatment capacity. And just to re-stress the point, composite samples will not accurately reflect the true compliance risk associated with these returns. Only online analyzers provide the true picture when considering compliance risk in all operational conditions. This slide is simply to show that there are further increasing pressures on the wastewater treatment works compliance. So the compliance pressures will only become more challenging in the future. So ammonia consents tend to travel in one direction, and that's not upwards, it's always towards zero. Future low phosphorus consents will have to drive a high chemical consumption, which could generate alkalinity issues, again impacting on the ammonia treatment capability of the plant. Energy prices are likely to remain changeable in the future and probably more extreme. Stud or triad periods are big opportunities to avoid elevated charges, but care needs to be taken when reducing energy consumption through these periods. Simply turning off aeration or reducing aeration without consideration is again a very risky strategy. Staffing levels are reducing and many years of experience have already been lost across the industry. Not mentioned here are the huge penalties associated with consent non-compliance, putting even greater strain on future capital delivery programs and the ability to meet quality drivers. But it's not all doom and gloom. There are methods available to greatly reduce this risk. This shouldn't sound radical, but it is a departure from the old-fashioned normal approach. Put simply, we should measure what needs to be controlled and control what is measured. So, measure ammonia and control ammonia. Using dissolved oxygen as a surrogate to estimate the correct treatment for ammonia is a very strange approach when you step back and actually think about it. By measuring ammonia at the inlet and the outlet of the activated sludge plant, you can use the full treatment capacity of the assets you already have, instead of relying on guesswork to achieve the right level of treatment. I'm probably showing my age here, but the old British advert goes, allow your system to be turned on and offable. And I think that applies to activated sludge plants, but rather than on and offable, I would argue up and downable, if you can forgive the English there. To illustrate the point, here's a graph of ammonia treatment rate versus dissolved oxygen concentration. It's normalized against DO at saturation point. So if we take the first line at 1.5 milligrams per litre, increasing the DO set point from this 1.5 level up to 3 milligrams per litre can increase the plant's treatment capacity by 25%. Obviously, the overall treatment is dependent on temperature, sludge age, and a number of other factors. But whatever the current conditions are at the plant, the base treatment rate can be increased by 25%. This is a very significant increase, which clearly provides scope to manage high load events. Further to this, by understanding the treatment rate required, it's possible to safely operate with set points considerably lower than conventional wisdom would dictate. So minimum DO set points of 0.7 or 0.6 can safely be used at times of low load. This approach provides greater treatment levels and saves on energy because the right level of treatment is always provided. This low energy treatment period far outweighs the energy needed at times of high load and actually provides enough energy savings for return of investment typically within 3 years. To illustrate the point further, here are two graphs. The top shows flow to full treatment and the lower shows the associated DO set points calculated by our nitrification real-time controller, or ammonia removal controller if you prefer. In this case, there's also a triad controller operating to minimize the energy penalties when electricity unit charges rise sharply. The short periods of elevated DO set points are to recover the design treatment step down associated with a triad period. Importantly, the minimum DO set points are delivered for approximately 60% of the time. This is not uncommon. You can see on the 21st of October, which is just to the very right of the graph at the bottom, that there was an extended rain event, and this caused the set points to deliver a maximum air for a number of hours to accommodate that load rate increase. Without that response, a final effluent ammonia spike would have resulted, but instead, the plant automatically responded and delivered the right level of treatment. So the nitrification system has been fully developed and implemented and is successfully operating in the UK, Europe and in the USA. But there are still misunderstandings within the water industry about real-time control. So moving on to the common misconceptions of real-time control, or advanced control, or just real control. Often you get people saying that it's simply a black box technology. Well, it is a black black box technology in the same sense that a car engine management system is a black box. You don't know the exact ratio of petrol to air, but you do know that if you press your foot a certain distance, you'll travel at a certain speed. I don't question the calculations of my car, as I can see the output of my actions and I trust the car's control. The real-time controller is exactly the same. The operator selects what concentration of ammonia they would like to leave the plant, and the plant responds. This is not relinquishing control of the plant. It's giving the site manager the tools to have more control than ever before. It gives site ops a real understanding of the plant and allows them to make good process decisions. Second, operations won't adopt the technology. It's a really important part of the commissioning process that we involve site staff to tailor the system exactly as they would like it to behave. We make changes together, we build up confidence and comfort with the system. This is supported with plain English guides and the knowledge that we are only a phone call away if there's any uncertainty. From experience, when an operator understands the benefits of the system, they don't want to return to their old method. The next is online analysis is unreliable. Well, online analysis can be unreliable if full consideration isn't given to the system. Large advances have been made with online analysis and, importantly, the filtration systems that enable the sample to be presented to the analyzer. We have systems that have been successfully in operation for many years, providing valuable process information, compliance security, and energy savings. There are some schools of thought that using variable DO set points upsets the biology or settling qualities of the mixed liquors. This is simply not true. We have nitrification-denitrification systems that use a period of 0 DO with perfectly healthy activated sludge biology. In practice, the controller will improve the settling qualities as over-aeration doesn't occur at times of low load, which often leads to filamentous bacteria dominating. Our sludge controller will improve biological conditions still further, but that's another topic and another presentation. Signal failures will cause compliance failures. Again, as previously mentioned, we work very closely with site staff to ensure that we have specific fallback strategies for the loss of every individual signal into the system. So this allows maximum uptime of the system and ensures that in the worst case scenario, the simple control that was in place before the advanced control is used. Energy savings are at the expense of compliance security. Consent compliance is always the most important consideration for this controller. It's only because we deliver the correct level of treatment at all times that energy savings are provided. You could say that saving energy is just a welcome byproduct of correct control, but the principal consideration is always consent compliance. So what do I need if I want to actually upgrade my plant? In terms of signals, the controller simply requires an ammonia measurement at the inlet and the outlet of the activated sludge plant, a suspended solids within the aeration basin, and a flow signal. These signals are pulled into a standardized controller using either a 4 to 20 millivolt Profibus or a Modbus network. I won't go into the communication protocols within this presentation other than to say it's an incredibly versatile platform. As mentioned previously, the software within the controller is completely flexible. It's simply a matter of entering local conditions within the program and the system is ready to be turned on. Commissioning of these off-the-shelf controllers, this typically takes about 1 to 2 weeks, so a system can be delivered and commissioned in around 6 to 8 weeks, providing either a rapid compliance solution or energy reduction program. This next slide is just to highlight where there are established RTC packages in use. To date, we have over 700 applications across UK and Europe. The map shows not just ammonia removal controllers, but phosphate removal, total nitrogen removal, sludge dewatering and sludge thickening real-time controllers. It's a good illustration of how much process optimization experience HACK has all over Europe. HAC is not only a provider of quality online instrumentation, it's been providing process solutions for many years across the whole of Europe. The risk of upgrading your plant to full control has been removed through this experience and the knowledge gained. So to summarise, if you've got wastewater treatment works with ammonia limits of 5 milligrams per litre or below, if you've got high strength returns or trade effluent issues or maybe tankard imports, if you've got a need to reduce energy consumption, then we have a controller that is available straight off the shelf and can be implemented very simply. Thanks for your attention. I'll now hand over to Jeff King, who, as he said, is the Municipal and Labs Sales Manager. He's been checking for any questions raised while I've been speaking, and hopefully we can fill in any gaps or clear up any points raised.
Thank you, Stuart. So yeah, we've managed to capture a few questions, which I will now ask. If anybody else has got any questions to ask, if you could please put them through in the Q&A box at the bottom of the screen, and we will go through them as well. First question I've received, Stuart, is can the plant be optimized with surface aerators?
Yes, basically wherever you have, whichever aeration method you use, whether it's FBDA or whether it's surface aerators, providing the plant can deliver the set point that the system requires, then then it's totally applicable to that site. So, for example, we've got a really good example up in Scottish Water where we've delivered a system which for a plant which has got surface aerators. In that case, we had over 26% energy savings, and more importantly, the site stayed compliant for the first time in over 10 years. So they had specific ammonia issues because of the very cold sewage treatment, because of the very cold effluent temperatures, and we were able to respond and provide the correct level of treatment there. So they're extremely happy with a surface aerator application up in Scotland.
Okay, thanks, Stuart. Second question is really related to the instrumentation, and are there any limitations on the instrumentation or existing instrumentation on a plant which may stop it from being potentially upgraded to an optimized system?
And that's respect to the measurement point itself, or?
Yeah, or the nature of the instrument. Are there any? We have different types of dissolved oxygen technology available. Does that limit the
right. Well, I mean, obviously, we'd like it to be HAC DO probes in there, but that's not a mutually exclusive thing. Basically, these systems have been designed to be really flexible to retrofit onto any plant. So if there's already an existing DO control, which is a completely separate system, we can simply sit above that system and deliver an intelligent DO set point, whatever instrumentation is available. Typically, it'd be unusual for a plant to have ammonia measurement already. If that was the case, then there'd be the potential to include that signal measurement. But what is important is to make sure that the signal measurement is robust. So obviously we've put a lot of effort into providing robust filtration to present a reliable sample to the analyzer. And everybody knows that if you don't have the correct ammonia signal, or if you don't have the right data going into a controller, then it invalidates the quality of the output signal. So in terms of signal, we generally go with the Amtax because experience has shown that that's a really reliable analyzer and gives us the level of confidence that we need to have a robust control philosophy.
And I think that probably leads on. There are three other questions we've got here. Trying to work out which is the best way to ask them. One question that's come through is, what happens if we don't have any ammonia measurements on either the inlet or the outlet?
Yeah, well, if you're providing the correct control, you need to understand what your ammonia loading conditions are, because that does dictate what your DO set point should be. So the system needs real-time ammonia measurement, and that gives a lot of benefits. First of all, it allows you to actually understand the true compliance risk that you're operating with. I think if every ASP had ammonia measurement on the outlet, then I think people would be less comfortable in the knowledge of the actual compliance risk that they are running a lot of the time. It's only the absence of that data which kind of which doesn't support the need to actually to act and actually improve the control. I think when you do have that information, it's definitely a motivating factor, I would say.
So minimum requirement really is an inlet.
Yeah, it's a minimum. Yeah, so because although the system has an extremely advanced algorithm which gives a very high quality feed forward signal, there may be specific local conditions. For example, there may be some form of inhibition from a trade effluent input, which would mean that the conventional treatment rate doesn't occur. So to make sure that the system is as robust as possible, we have an ammonia measurement on the outlet of the plant, which can then correct for any anomalies that may affect the biology, which you couldn't account for in a normal in every event with a biological model that we have in the controller.
Okay, and so with the minimum requirements of an inlet and an outlet ammonia monitor, maybe you could just give a little bit of an insight into a preference with regard to, say, an analyzer and a probe, because again, there's different technologies available for measuring and monitoring ammonia.
Yeah, we always use wet chemistry analysis. We've found that is, in the UK at least, we've found that it's by far the most robust method. There are ion selective electrodes available, but they can work well, but they need a lot of attention. And I think what we aim to provide is a system that helps the plant, and actually, isn't. We don't want the plant to be seen as something that is extra work for the operator. The controller actually is helping provide the right level of treatment and helping the correct process decisions to be made to actually free the operator up to do other important work as well. So it's for us, we've got great experience using wet chemistry analyzers along with a robust filtration system.
Because that leads to another question that somebody's asked, which is, can you tell us about the maintenance requirements? So I think you've just maybe touched on that, but the maintenance requirements, if you have a wet chemistry analyzer, will be quite different to those if you had an ion selective electrode.
Yeah, well, you've got basically you've got a service visit every three months, which essentially is to replace chemical reagents and things things like that. The actual filter itself is designed to be used in a crude sewage application, so it's extremely robust. It could depending on the site, because every site's different, it could maybe go 2-3 weeks without a change. But in practice, we advise just changing it over once a week to make sure. Basically, then it becomes habit forming. If it's every other week, then experience has shown that it tends to get forgotten about, and then that can become a problem. But the actual swap out procedure of the TMS filter is super easy. So you simply, the filter that's in duty, you just take that out. It's just on a flexible hose, so there's no awkward lifting or anything like that. You simply take the filter off and store it in a cleaning solution. You then swap out the filter that was in use beforehand. That's been soaking in a cleaning solution, and then that you basically attach that. So you've always got one filter cleaning and always one in duty. So you simply swap them out, and we've found it's because it's so easy and because it's so quick, it actually does take place. So that's a common worry is that they're going to be difficult systems to maintain, but that's just not the case because we have got such robust filtration, and it's so easy to actually swap things out that it does take place.
Okay, thanks, Stuart. A few more questions here. When investigating a potential ammonia failure in the final effluent, what methodology would HAC recommend to adopt to come to this conclusion?
Oh, could you just repeat that again? Sorry.
Yeah, when investigating a potential ammonia failure in the final effluent, what methodology would we recommend to adopt to come to this conclusion?
Well, if you've got an online analyzer on the activated sludge effluent, then you can do a straight mass balance, and you're in a nice position that you've got complete visibility of how the process is performing. If you don't have that, then really the next best thing that you can have is maybe say a 20. If you know that you're getting problems, you could adopt a 24-hour composite sample, and you'd have to take hourly spot samples, which isn't ideal. It's not an ideal position, but then it still gives you a greater visibility. So obviously we've got the LCK vials and the DR 3900, which is the lab application, which is extremely easy to use, and you can get the spot samples analysed in an hour or so. So yeah, the more quality data, the better is the simple answer to that. And again, it's difficult to without understanding what the loading conditions are on the activated sludge plant. It's difficult to understand the treatment shortfall that's actually been experienced on the plant. You can obviously do mass balances and adjusting for retention time to try and identify when you think the actual the point source was actually hit the works. But again, this is something that's it's not a quick thing, and it kind of takes us back to the point where you're spending a lot of time doing an autopsy on a failure rather than having the information up front and being able to make the correct decisions for the activated sludge plant before it becomes a problem. There are methods to try and establish what the root cause of an ammonia peak was, but yeah, without good quality data, there is always going to be an element of uncertainty around whatever your findings are.
Okay. As a follow-up to that one, the same person's asked another question. Would it be sufficient to test the supernatant of activated sludge leaving the ASP to give you an idea of the current ammonia that's actually leaving the plant?
Yes, well, that's what actually is measured. So we measure the feed into the activated sludge plant, and we measure the outlet of the activated sludge plant. So by measuring exactly what's coming off the back of the activated sludge plant, I mean, within the software, again, it's totally configurable. So if we're forced to have a measurement point that is before the return activated sludge comes in, or if there's a flexible configuration which then automatically accounts for a number of different points where you can actually measure the ammonia, just to make sure that it's applicable to all wastewater treatment sites. So yeah, because we have the TMS filter, then we can pretty much measure in the aeration basin. If, for example, the overflow is, I mean, we've seen that in certain plants. They've spent a lot of money building a plant and then saved money by not having the walkway all the way to the end of the actual lane. So that made getting a measurement point a little bit more problematic. But obviously, what we chose to do in that case, we had a measurement point that was maybe 200 meters away, but because the activated sludge plant was on a huge hill, the retention time between our measurement point and what came off the end of the activated sludge plant was in the order of seconds, really. So we could reliably use that signal because it was still, there wasn't a great deal of lag with that, and we could build that into the commissioning process to make sure that the feedback loop was accurate.
Okay. Another question. This is more one relating to the impact, I think, of having a variable DO. When the system drops dissolved oxygen levels at a slack period, when that's not needed for removal of ammonia, does that present a risk for a potential breach of BOD or COD?
No, because generally, as I mentioned in one of the early slides, because the rate for BOD or COD removal is proportional to the actual load, that's almost self-leveling. So as a BOD or COD increases, providing you've got an excess of dissolved oxygen, then the actual BOD or COD treatment rate will automatically increase. The danger you would have is if you had an extremely high load that hit and you had a DO, just say you had a minimum DO set point of 0.4 or 0.3, something like that, then you might find that it automatically overwhelms what the aeration system is able to provide for a short period of time. And this is why it's important for us to speak with the operators and actually gain that experience. So we kind of hold the operator's hand through the commissioning period, and often, because if a plant's been run at, say, 2 milligrams per litre for 10 years, when you mention that, you think the plant can run at 0.7 or 0.6, eyebrows are raised, and there's the sort of disbelief, oh, this will never work. But because the operator's got complete control of the operational band which the calculation puts out, so we can say, okay, well, what we'll do in this case, we'll have an acceptable output from the controller to, say, 2 milligrams per litre to 1.8 milligrams per litre. And then you'll see that it's always at 1.8, and then you slowly open up that band and demonstrate that all the parameters are still well within consent, and that then allows the operator to gain more and more confidence with the system. So again, just walking slowly. So it's even though what the operator doesn't want to see is somebody who's come on the plant a fortnight ago telling them how to run their plant. That's not That's not the right way to approach it, because there may be things that we need to consider as part of the commissioning process, and the operators, are by and large, they do know the conditions of the plant well. It's just, again, helping them understand that the correct DO set point for 5 o'clock in the evening, say, is not the same correct set point for 5 o'clock in the morning. So in terms of, because we can control what that minimum DO set point is, or to put more correctly, the operator can decide what level that is. They can experiment to find out the level that they're happy with themselves. So it's we've created the controller for the plant. It's when it's active on the plant, it's not our controller, it's the ops guy's controller. He then tailors it to exactly what he wants it to do. So if there's any concern that having a minimum DO set point of 0.6 is problematic, he can just raise that to 1 or 1.5 if he likes. It's their decision to make to balance energy consumption with compliance risk. And if they choose to do that, then we can give our opinion and our advice on what we think the correct parameterization of the software is. But at the end of the day, it belongs to the operator, and we help them and advise them. But it's their decision at the end of the day, and we have to respect the way that they want to run their plant.
Okay, and just going back to the analyzers, I think maybe it's not clear exactly what type of analyzer we're referring to. So the question here is the proposed wet chemistry analyzer an inline system measuring from a side stream, or are we referring to a laboratory analyzer measuring effectively grab samples?
Right. So the analyzer that we use is the AMTAC. So it's a wet chemistry analyzer, inline analyzer. It's designed to be out in the field. So it sits within its own weatherproof cabinet, sort of at the side of the sampling point. And then the way we provide the sample, there's a number of different filtration options we have, but basically it's essentially a flexible hose that goes into the flow, and then simply draws the sample and presents it to the AMTACs. So we've got options of high ranges or low ranges. So if it's an unusual crude sewage, then we might use the AMTACs with a, say, 0 to 100 milligram per litre range. And for the final effluent, we typically use the low range AMTACs just to make sure we've got the greatest accuracy possible for the outlet reading.
Okay, so I think that's clear, Stuart. So it's definitely an online analyzer.
That's right.
Another question here, which is relating really to sort of potential process enhancements. You mentioned, given the nitrification, you mentioned that the given nitrification rate can be utilised better with the RTC. Therefore, would you expect an enhancement of the nitrification rate of a plant after installation of an RTC due to optimal growth conditions in the ASP?
Yeah, you can. I mean, you're not going to change the fundamental biology of the plant, because that's simply what the controller does. It understands the kinetics of the growth rate or the ammonia uptake of the biology. So to do that, you need to understand how many workers effectively you have in the aeration basin. So the controller will have an understanding of the sludge age, and because if we look at the slide, let me just take me back to the slide here. So because we've got a mixed liquor, a measurement of the mixed liquors within the aeration basin, so that gives you a kilograms of total biology. Then you have an estimate of the sludge age. So of that biology, you know that X% will be nitrifying bacteria. So then that allows you to know how hard you've got to work those bugs to make sure that you're achieving the right level of treatment. So the controller doesn't alter how the bugs behave. It follows what the bugs are doing, and if you like, so the biology determines the rate. What we also have, which we've not covered in this presentation, is a sludge age controller. So if you want to alter the rate, or if you want to optimize the nitrification rate, then we would recommend a sludge age controller, and it's kind of not really got the attention I think it deserves in the UK, because historically we generally look at a fixed mixed liquor level and kind of fix that. So, commonly just say 3,000 milligrams per litre of mixed liquor. Now, the sludge age in winter at 3,000 is very different to the sludge age in summer. Even though you've got a theoretic what looks like the same conditions all year round, because you're hunting to a similar milligram per litre level in the aeration basin, what you've got considerably different operating conditions throughout the year without even realizing it. So what we have a controller which allows you to dial in the optimum sludge age, and that's based on the temperature of the sewage. So there's a direct relationship between temperature and the correct sludge age that you can run with. And in those conditions, what you can find is, certainly for a common problem you have is people will increase the mixed liquors to a very high level when they are receiving high loads, and sometimes the aeration capacity of the plant isn't able to match the entire biology that you've got in there. So you have a sludge age that's far too high, a lot of bugs that are just sat there with indigenous respiration, not doing a great deal of treatment, but grabbing the oxygen before the delicate nitrifiers can actually utilize it. So in those cases, a sludge age controller would really help, because you know that you're providing the right balance of both carbonaceous and nitrifying bacteria, and you're not generating additional biology in there that doesn't contribute greatly to your overall level of treatment. So yeah, it's not a rapid answer, I appreciate that, but the nitrification controller provides the right level of treatment for the biology that you've got. The sludge age controller manipulates the biology you've got to give you optimum conditions.
So with a standard upgrade minus a sludge age control, you will ensure compliance of the plant by applying the correct amount of dissolved oxygen. However, with the sludge age controller, you ensure the compliance, but in a more efficient way, so probably saving a little bit more energy.
Yeah, there's certainly more energy to be saved, because you're not providing additional. Obviously, if you've got a lot more bugs in the system, there's a lot more respiration, so then you've got to provide greater levels of oxygen just to maintain whatever DO set point is the correct set point.
Okay, I think that's clear. And that leads on to, we've only got two more questions, which I guess are more related to the how we set up the system and the potential payback. But we've talked primarily about compliance in today's presentation, and that's first and foremost is to ensure compliance of ammonia and minimising the risks. But with the sludge age control, you talk about, you've touched on the other element, which is the potential energy savings. And what's a tip? Can you gauge what the typical payback would be for somebody who installed a advanced control system to a wastewater plant? Is there
I think typically we see between, say, 15 and 30%. I mean, it's very much dependent. Every site's individual, so it depends on how well or otherwise the site was run in the first place. But from my experience, 25% is more common than not. So at a very basic level, if you know your aeration costs, then if you apply a 25% saving to those, then it's as a kind of fag packet calculation to work out what you could expect to save and what the returns of investment would be. 20, or maybe say 20% to be on the conservative side, perhaps. But yeah, that we would expect between 15% very conservatively, but more often than not between 20 and 30%. Specific energy savings in aeration, and obviously aeration costs, are typically about 50% of the entire costs of the wastewater treatment plant itself. So that's it's the big return item that you can actually make an impact very quickly on a plant.
Okay, and that leads to the final question, Stuart, which is, I guess many people see real-time control systems as quite complex and involved, but how long would it take, again, on average, to install a simple nitrification real-time control system?
Yeah, so in terms of, we've got how long's the lead time on instrumentation itself? So yeah, so you've got a lead time of say 4 to 6 weeks on the instrumentation. The RTC, because it's kind of an off-the-shelf unit, the standalone units, that's going to be a similar time as well. So they can be on site with between 4 and 6 weeks. The commissioning itself is maybe 1 to 2 weeks. We can take longer than that if the site requires that. I think the important thing is to walk the site guys through the process at the rate that they want to go. So, in an ideal world, we'd simply be believed when we said, right, these are the set points that we think you can run at, and you could put those straight in there. But in practice, we always go more slowly than that, because we've got to respect the concerns of the plant operator, and sort of walk them slowly. And it's a healthy thing to do as well, because then that the output of the system is being closely watched, and when they see a peak coming into the plant, and then they see the output of the plant exactly as they've put a target set point in. So if they've selected 5 milligrams per litre, and they see a high load coming in, and they see 5 milligrams per litre going out, generally, it's a bit mind blowing if you've not been in the position to do that for 15 years. So yeah, in total it could be 6 to 8 weeks. Maybe 8 weeks. I would say from placing the order to being in a position to actually run the plant.
Great. Well, thanks, Stuart. Thanks for the presentation. Really interesting, and for also fielding all of those questions. Hopefully, everybody has taken something away from that. So just before we close, I'd just like to remind everybody that we do have another webinar coming up, the next one in our series. Again, focused on real-time control, but this time we will be looking at phosphate, and it will be Martin Butterfield who will lead through that presentation, and also give reference to some success stories and case studies in the UK. So thanks for everybody attending. Hopefully you found it useful. If you do have any other questions or want any further information, please feel free to contact us directly. And have a great day. Thank you.